Hi, everyone, and welcome to the webinar. Thanks for joining us. My name is Tom Mitchell, and I'm with Cloud Academy. In today's webinar, we're focusing on serverless containers. Containers have become the standard for app deployment processes, and Kubernetes has emerged as the standard for container orchestration platforms. When running Kubernetes at scale, managing, operating, and scaling its infrastructure to maximize cluster utilization without suffering from idle resources can be a big challenge. There are simply too many things that an operator needs to manage and configure, such as selecting the best instance type, selecting the instance size, determining when to scale up, when to scale down, and making sure all of the containers are scheduled and running on the best instances. And that's all before even thinking about the cost and resource optimization. Today, we're going to discuss how you can run Kubernetes workloads on any cloud platform without managing infrastructure. Today's agenda will include a container service overview, followed by the challenges of container infrastructure. We'll then cover the power of excess capacity, and then rounding things out, we'll get into a detailed and technical demo of Spotinst Ocean. Before introducing our panelists, I just wanted to let everyone know that this webinar is being recorded and that all attendees are going to receive that recording as soon as it's available. We'll also be holding a Q&A session toward the end of the webinar, so if you have any questions, post them in the chat box and then we'll tackle them during the Q&A session. On our panel today is Kevin McGrath, the Chief Technology Officer at Spotinst. Joining him is Tomer Hadassi, the Solutions Architect Team Lead at Spotinst. Thank you both for joining us. These guys are going to do most of the talking today, and they'll be guiding you through the agenda topics in detail. So over to you guys.
All right. So hello, Kevin McGrath. So we're going to talk a little bit about Spotinst. We're going to give you a little, for those who don't know Spotinst, we're going to give you a quick introduction. Then we're going to go right into level setting everybody on the call because everyone comes from different backgrounds. So we're going to level set on containers and Kubernetes and kind of how we got to the space that we're in today. And then Tomer is going to take it away and really dive in depth on what scaling and what we mean by getting to nodeless or serverless containers towards the end of the talk. So with that said, company overview, Spotinst was started in 2015. Since then, we've had a couple of rounds of funding. We're expanding today. We're doing well in over 4 locations around the globe, 150 employees with over 1,400 customers. We measure ourselves in what we call resource hours per month. Customers come to us for cost reduction and workload automation, and we've been steadily increasing our resource hours since 2016 and are managing over 3 billion resource hours across all the major cloud providers. So with that said, let's get to it. We're going to start off kind of, again, what I said with a level set. We're going to go into why containers. And I know this is kind of pulling it back pretty far, but I want to build up everybody on this webinar so we're all at the same point from start to end. And containers really became popular a few years ago with Docker coming out. There were some other companies like Google who've been using it for a much longer time with things like C groups. But Docker really came out and showed us how as an industry that we can have somewhat of a platform independence, and we can build applications once and run them anywhere. And these containers contain all the dependencies of an application, and they have an abstraction of the underlying host OS and the underlying infrastructure. And with that, these containers are freely movable from a person's laptop all the way up to the cloud to where they run in production. For the most part, containers are lightweight and efficient. They're much more lightweight than VMs. VMs in general can be gigabytes, whereas containers, when built correctly, are mere megabytes. This is not to say that someone can't go out and build a very large container that's a gigabyte big, but in most cases, you're trying to keep these containers as small as possible and keeping the footprint as small as possible. They're easy to package and easy to deploy with a few commands from a DevOps engineer or developer. An automation script or someone's fingers can easily package and deploy a container at ease. They provide effective isolation, not necessarily as much isolation as a virtual machine, but especially for applications that all run within a single organization or within a single security paradigm, they provide isolation between container and container amongst the hosts. Also, speed. Containers are fast. They're much faster than a VM when they start. To start, create, replicate, or destroy containers can take seconds or even microseconds, depending on how fast your build system is. This is great for iteration on not only development, but also on cycles to deploy to production. And finally, because of all these features that you see above, you have improved developer productivity and development pipeline. You have a very structured way of getting code from a developer's hands to production and having it be in the same state as when it left the developer's hands. We don't have as many different builds and changes along the way as a developer moves from development to staging to production. Developers can have a much more reliability that their code is going to behave in production exactly as it behaved at their fingertips on their laptops. Which brings us to why Kubernetes. This is going to be a major part of the talk when Tomer takes on later. But as we kind of decoupled our services and we made these microservices and we made these containers as small as possible, there was a growing need to know where all of these microservices were, how to place them into the environment, what infrastructure should they live on, and how do they necessarily get orchestrated as an application. And this is where Kubernetes came into the picture. Originally out of Google, in the spirit of what Google calls their Borg, Kubernetes was created on how Google operates and how Google managed containers for a decade before kind of the mass market had adopted containers. And what you can see here is there is a master orchestrator with an API server, scheduler, and controller manager. And that is taking care of all of the worker nodes and infrastructure that is out in the environment. And the labels that you see on the diagram where are pods are where the containers are actually running. And what's very important here is you're not always necessarily dedicating a pod to a particular instance. And these containers, because they're movable, because of all of the options that we told you about containers in the previous slide, these containers and pods can kind of freely move amongst the infrastructure as long as that infrastructure provides the minimum capacity for that pod or container to run wherever it's moving. And this is what Kubernetes does. Kubernetes kind of takes inventory of what's there and tells the infrastructure, hey, run this pod, run this container, scale this. What is the health and what's going on in my environment so I can make this application highly available. So lastly, we talk about containers, we talk about Kubernetes, and the adoption rate has been very big, right? We have, for the past 3 years here, enterprise adoptions of containers via Kubernetes specifically, and you can see how enterprise organizations continually adopt more and more, not just containers, but containers with Kubernetes. Kubernetes, as a lot of people would like to say, is become a clear winner in container orchestration and is how most enterprises are moving forward today. So to bring it to a practical level on what you can do with containers in the public cloud specifically, all 3 major cloud providers, AWS, Google, and Azure, offer Kubernetes as Kubernetes services, specifically so you don't have to run the management layer of Kubernetes. So this is the first part of going serverless or nodeless with Kubernetes. The first thing that you don't want to manage with Kubernetes necessarily are the masters and the control plane of what's going on. You want someone else to kind of take that off your hands so you don't have to hire the large DevOps team or the engineers that it takes to run the management of Kubernetes itself. It can be quite heavy for large production environments. In AWS, the service is called EKS. In Google, it's GKE. And in Azure, Azure actually has 2 ways that we can deploy in both AKS and AKS Engine. Azure's service is neat when compared to the other 2, in that AKS is an open source version of actually how they deploy Kubernetes as Azure Container Service or Azure Kubernetes Service. So that open source project, what they do there, you can actually see how they add features to that project and how it makes its way to the service itself. So now we're going to dive in to specifics for each one of the cloud providers. Amazon Web Services, as I said, has Elastic Kubernetes Service, or EKS. They have another service called ECS, which I'm just going to mention because it happens in the container space. But adoption of EKS is higher than that of their older container service. The workloads can be ported to other clouds. Because of the Kubernetes aspect, you're not necessarily tied in. AWS supports Kubernetes as Kubernetes exists. You can take a workload that's running on-prem, for instance, your on-prem cloud, and you can deploy it to Kubernetes and AWS, and the Kubernetes environments act the same, depending on what environment they're in. We have integration with other AWS services. Integration with other AWS services is limited, and underlying infrastructure needs to be managed by the user. Because it is more of a pure play Kubernetes and not the service of ECS before it, you do need to use the native Kubernetes bindings to the AWS platform. So if you are an AWS user today, there are a couple extra hoops to jump through to make sure that you're getting that full native AWS experience. User management requires AWS IAM. This is a very important part when going and running Kubernetes on top of AWS, that AWS has really integrated their IAM model into how you use, deploy, and configure AWS. You will need to buy into this model, and you will need to buy into using AWS IAM to successfully run EKS and AWS together. It's something that you don't necessarily have to do with a vanilla install. There is some lag between the latest release of Kubernetes and AWS support. This can be looked at as both a good thing in the fact that AWS is vetting releases before they go out. You also will have to wait for those releases for a little bit of time before you get the latest and greatest features on AWS. Lastly, Elastic Container Service. It gets an honorable mention here. There are a lot of users on ECS. We want to call out the fact that AWS does have another container service. It's a proprietary orchestration engine and integrates a little bit more smoothly with the rest of the AWS platform. Moving on to Google Cloud. Google's offering is called Google Kubernetes Engine, or GKE. They are the original authors, or the original authors come from Google, and GKE always has the most recent version of Kubernetes. This is because it's being built in-house. They're testing it, they're deploying it, they're running it. Google will have the latest version of Kubernetes in very short fashion. The infrastructure is more adaptable to the Kubernetes infrastructure. At Google Cloud, Kubernetes and the infrastructure are more baked together than in maybe the other clouds. And there is native integration with Google Compute Engine services, as well as Istio Service Mesh and Linkerd, which are popular ways to do service discovery and application management within Kubernetes. There's also an on-premise option available with Google Cloud. Last but not least is Microsoft Azure. Azure, as I said before, has two offerings: the Azure Kubernetes Service, which is priced based on the underlying virtual machines. It is a service that will run the virtual machines for you, but you don't necessarily have access to them. And then there's also AKS Engine, which is an open source version of how they are running AKS. If you need fine-grained control of installation and configuration of worker nodes, AKS Engine provides you very, very low-level access to how Kubernetes is being built and deployed. You can run your own master servers and your own nodes, and you can get a fully customized level of support out of Kubernetes that way. Azure also provides full support, obviously, for Windows containers if you're using those today. So we've talked about the different aspects, the different services from all the different clouds that are offered, and how controller layer to you, so you don't necessarily have to manage it yourself. What we're going to get into now is at the worker node level, there are some struggles with Kubernetes. primarily being under the infrastructure. Because of the way that you deploy pods and containers to Kubernetes, you're now scaling at two different levels. And Tomer is going to go into more depth on this later in the deck. But what you're looking at is your app needs to scale at a different level that your infrastructure is scaling. And how you pair these two scaling mechanisms together to get the most optimized performance can be a struggle for a lot of people who are running Kubernetes in the cloud. Also, there's something that's called lifecycle management. Lifecycle management is the life cycle of the infrastructure itself. How long does the infrastructure actually have to be around, and how long do the pods on top of the infrastructure need to live, and can they move around? So life cycle can mean an on-demand instance, which is around 99.9% of the time and up most of the year. Life cycle can also mean running on extra capacity, which is spot instances in AWS or low priority VMs in Azure or preemptible instances in Google. These instances aren't necessarily up with a 4.9 SLA, but can easily save you up to 80% off the cost of your infrastructure as pods freely move from instance to instance as they come and go. There's also a struggle with pod right sizing. And what we mean by right sizing is developers knowing how much memory and CPU are actually needed by pods before they get deployed out into the infrastructure. Often we see with Kubernetes, a lot of engineers just kind of giving a good blast radius for their application so they know it's going to run. Actually knowing what it needs to run in production and then right-sizing those applications so you're as efficient as possible with your infrastructure can be a long manual task. And then lastly is multi-cloud. A lot of customers will look to have different applications in different environments or even different clouds depending on the dependencies of those applications and how to control Kubernetes as it does cross clouds. UI is also a concern for a lot of people who use Kubernetes. A lot of people look for more visibility into what's actually going on with the pods and containers that are running that comprise an application. This is why you see a rise of things like Istio and other applications to give people more visibility on what their applications are doing within the environment. Storage is another concern, where Kubernetes itself has some very generic cloud storage providers. Every cloud provider has their own implementation of how to use storage within the cloud. There are also third-party providers. Now, it's very important here, especially when you're going serverless and nodeless, how to get your storage to move with your pods where it needs to go. How do you take an elastic block store? Or how do you take a provisioned disk on Azure? How do you ensure that disk is going to find the pod and the infrastructure that it sits on? And not only that, when you're scaling, how do you prevent these volumes from being scaled quickly? These are all things that you need to keep in mind, as well as replication, if you were to do it yourself. But if you have a system that knows how to look at this and knows how to do it for you, you can care less about the infrastructure that's underneath. Much like storage, there's networking, and there's native networking that comes within Kubernetes, or native networking that comes with the clouds, where you use the actual elastic network interfaces directly, or there's overlay networks. Each have their advantages and disadvantages, and you need to know how you're scaling each so you can understand how many ports, IPs, different things that are underneath. These are things that you don't want to care about at the end of the day, and this is where we want to get to with what we call serverless or nodeless Kubernetes. So at this point in time, we are done with the level setting and kind of the general background on, why we started with containers, why we've moved to Kubernetes, what the major cloud providers are offering, at least from a control and management plane, what the struggles are to run worker and application nodes within Kubernetes. And I am going to turn the rest of the presentation over to the very capable hands of Tomer, who's going to take you into a deep dive of Kubernetes and infrastructure autoscale.
Thank you very much, Kevin, for this wonderful overview. So now that we've heard about all the different clouds, kind of the last piece Kevin left us with is that really there are some challenges when we are trying to auto-scale and manage infrastructure in Kubernetes, regardless of the cloud of our choice. And that starts because we have two different layers of scaling. The regular layer, which is the infrastructure. What we normally know is the infrastructure as a service, scaling using auto-scaling groups, using some different thresholds based on CPU and memory. But Kubernetes scales differently. It scales on a container layer, in an app layer. It doesn't do step scaling where it gets another 1 or 2% of resources at a time, but rather deploys new pods and adds more replica sets into your cluster. And basically sends bulks of workloads that could have a specific allocation of resources available to them. Because of that, we're going to end up with these two separate layers. One, decided by all your developers on how their application should scale according to what metrics, whether that's the number of requests incoming, the CPU, the memory, and so forth. And then you as an operator have to manage one underlying infrastructure that will be able to capture all of the needs of your developers, regardless of the configurations they've set. Your developers are going to use the Kubernetes HPA many times. That's where they're going to put their scaling policies on the app level, or they will even manually run deployments and increase replica sets in order to better understand and better cover the needs of their application. With that, we end up with a pretty big problem. We want to meet these application demands, but at the same time, we want to minimize the idle resources, eliminate waste, and making sure that this cluster is as cost-effective as it can be, and has as minimal overhead as possible in the management of its infrastructure. At the end of the day, we started adopting containers to free our developers, to free our time, and to be more dynamic and flexible, not in order to start managing infrastructure in a very complex and unclear way. Underneath that, there are three different layers. One of them is the instance sizing. Which instance do you use and when? So we just mentioned, different developers will deploy different containers. This can be, we've seen up to hundreds of different deployments in a single cluster deployed by hundreds of different developers, each one of their own choice. You can provide all of them with a single instance type and size. So how do you right-size the instances? Then, as Kevin alluded to earlier, how do you think about the instance lifecycle? Is everything going up in reservations? Are you running on-demand servers? Or are you going to use the cloud access capacity to enjoy the piece from there? And the last layer is really the right sizing of the pods themselves. After you use the right instance at the right time, in the right life cycle, you have to make sure that the pods themselves didn't have the wrong definition and ask for way too much or way too little resources. So let's begin with the instance sizing layer. The instance sizing layer basically refers to the idea that you need to right-size the instances and scale them up at the same time while running on Kubernetes, getting these different containers. Let's start from the beginning with the classic method. Step scaling, what we all know from starting in the cloud, Azure scale sets, AWS auto-scaling groups, and so forth. When a metric exceeds its threshold, either CPU or memory, we're going to add or remove instances. Pretty straightforward. We have a policy, let's say, at around 75% of CPU. Whenever we spike up above that, we add more instances, the average usage drops. We have a scale down policy at 65% CPU. Whenever we drop below this threshold, we remove an instance or two, the average utilization increases. This works great when you run a single application running on top of images that are being deployed to these servers. When you run dozens of containers on each one of the servers, and when your deployments can happen in a way that more than doubles your cluster all at once, you don't want to scale up like that because you will basically get stuck in a cooldown hell where your cluster can scale up, wait for a few more minutes, and then only then scale up again, doing only 1 or 2 instances at a time when it's time to add 50. And it will take hours to finish the scale. A more sophisticated way to do it will be to do some Tetris scaling. We'll use a few instance types and a few sizes, and use the right instances at the right time in a bit more of a sophisticated way. With that, we also have some challenges. So let's take some examples. We have 3 different instance types, and there are a few sizes of containers coming in. A new container is coming. It requires 3 units of work, and as we see, there are 4 units available in the cluster. The cluster is not going to try to scale up because there's enough resources, it's not hitting its threshold, but this container can't really fit in any one of the instances fully, and it can't split itself in half and deploy itself across the containers. With that, the container is stuck in a pending state, and you have to either manually release the container or manually add a server. Let's take another example. Let's say we have two instances. Again, we have a pod pending. We have 2 units of work. We're missing one. We definitely have to scale up now. Now we scale up, and we added another instance that was too small. We have enough resources in the cluster, but not enough resources on any given instance again. And the same story, the pod gets stuck in a pending state. And let's take another example when we scale down. So you can see there are currently about 9 units here. Only 4 of them are in use, so there are 5 free units. With that, you can probably scale one of the instances, and we go ahead and we scale the largest instance. Now, again, there are enough resources in the cluster to handle all these pods, whether that's the 2 small ones and the big one, but not enough on any given instance to handle that big pod now. And again, the cluster is stuck and has to manually be released. With that, we actually believe there's a better way to scale. We believe that the smartest way to scale Kubernetes is actually driven by your containers. Each one of the developers defines what their application needs. Great. What if we can also scale and provide servers based on that requests? Basically, let's stop thinking about the nodes themselves, focus on the containers, focus on the application demands, and make sure that we can always meet them in real time. What does that mean? We want containers to be the first-class citizens of our clusters. We want the instance size, its type, and its life cycle to be determined based on the pod coming into our cluster. The pod will hold the containers inside of it. At the same time, it's extremely important to honor all the layers to take this into account whenever we scale up in order to make sure that the cluster is as effective as possible. Another thing we want to do is we want to be driven by the pods when they have special requirements. We don't want specific pods to live in specific auto-scaling groups that can support GPUs, but rather give GPU-driven instances when a pod comes and requires a GPU. If a certain pod can never withstand an interruption, it's more of a legacy application that was wrapped as a Docker container, we can take it to be an on-demand instance and make sure it will be provided with the right machine at the right time. With that, we will enjoy very effective and low overhead clusters. And that will achieve us the nodeless, or what we normally call serverless. Kubernetes calls nodes, so we call it a nodeless experience. This means we don't have to manage any of the underlying infrastructure. We do not choose the instances anymore. They're simply coming when they're needed. We're scaling in real time based on the requests and the requirements coming from our end users, which is the developers in our organization. Part of being serverless is having utility billing. We're not paying for stuff we're not using. We're only paying when we have requests and we actually have load on the servers. With that, we also want to be able to scale all the way down to 0. If certain namespaces and certain deployments no longer need infrastructure, that infrastructure shouldn't be there. At the same time, scaling should be extremely fast and be very responsive. So if you went down from 0 pods in the morning to 1,000 pods as markets are opening at 9 a.m., your autoscaler should immediately realize that this is the total number of resources that you need. And with that, make sure to scale up enough instances at a single event to answer all of that without you ever needing to get involved again. That throws us into the next layer. So now once we got our nodeless experience, we got the right instance at the right time. Now we need to think, how do we want to pay for that instance? I want to pay a full price and an on-demand rate, get the 4.9 availability from Amazon, but pay the full market prices or from any other of the cloud providers. Do you want to make commitments and pay for the reservation or committed units, pay the cloud providers upfront or make some commitment for 1 to 3 years, get a certain level of discount, but lose a lot of the flexibility that is natural for containers and Kubernetes that we, to begin with, adopted them because of. And we have the third pricing model, which is the cloud provider's excess capacity, which allows us for a lot of cost optimization. They're known as spot instances in AWS, low priority VMs in Azure, and preemptible VMs in Google Cloud. These are basically the excess capacity in the cloud provider's data centers. According to the information they've shared with us, it's about 40% of any given data center is excess capacity. which means you can get the exact same instance type, size, and family for about 70 to 90% discount of the on-demand price, with no commitments, no payments upfront, and nothing of that sort. The one main caveat, the hyperscalers will no longer give you an SLA on the instances, and they will be able to shut them down with a 30-second to a 2-minute warning, depending on the cloud provider, and take your instances away from you. However, smart management of these instances can provide the deepest cost savings inside the public clouds, much more significant than reserved instances, much more flexible. To get a cost-effective dynamic cluster running containers. We do have to plan for the interruptions a bit. Simply containerizing something does not mean it can withstand an interruption. We need to remember that these instances will be preempted, and they will have different mechanisms, and we will have to manage them differently across the different clouds. But with a deep understanding of the capacity pools, the markets they're working with, the regions that we're playing, and the instance types and sizes, we can with no problem maintain 4 nines of SLA while running clusters fully on excess capacity across different cloud providers based on the application demands. And with that, now that we solved both for which instance we're going to use when, how are we going to pay for that instance, we have to make sure that to begin with, the requests were correct. With that, we want to do some pod right sizing. We want to check the pod metrics every 10 seconds or so, aggregate some averages and information. And once we have all the aggregated data, right size the pod, redeploy it. They have to be restarted in this case. See that this time it's hitting its metrics better and properly utilized, and then we can defragment the infrastructure again based on these new pods. What are the advantages of having a serverless SaaS platform, container as a service? So now that we've solved all 3 problems, we have a pretty sophisticated infrastructure. What is that going to give us? First of all, improved productivity. We don't have to manage it again. It's now a fully managed containerized platform. All the infrastructure is managed by the platform of your choosing, and which we will share how we do it with Ocean. The masters are managed by the cloud providers, and you enjoy an infrastructure that really does not require management and can give a lot of liberation to all of your developers. It's simple to scale because it's following the application demands in real time. As more developers and more applications are joining that Kubernetes platform you're providing in your organization, you do not have to modify it, you do not have to change it. As you're adopting different cloud providers, or as you're lifting from your on-premise containerized cluster to the cloud, you do not have to manage machines, and it's very easy to scale across any of the providers. And of course, you'll get greater efficiency and cost management because you will control the cluster in real time based on its needs. With that, I would love to share how we do it with Ocean. Coming from all these problems and all these issues, we as Spotinst built a serverless container experience. We call it Ocean. That's the general architecture of Ocean. Ocean will take any one of the control planes that you have on Kubernetes today or on ECS. That's including Amazon EKS, Google Kubernetes Engine, AKS, really any flavor of Kubernetes, or even Red Hat OpenShift. Ocean will wrap around all of your worker nodes, knowing how to spin up the right node at the right time based on the application requirements. That means you have no VMs to manage. You do not need to choose your instance types and sizes anymore. Your infrastructure will be significantly cheaper because we will reliably leverage spots, preemptible, or low priority VMs, depending on the cloud provider. We will handle all of the background processes of making sure their availability is there, the rates of interruption are low, the instances are being drained, the workloads are moving from one node to another. And we have been doing so for the past 4 years. In addition to that, everything will be supported using APIs and a CLI, as well as a robust UI to give you deeper analytics and understanding of what's happening in the cluster. and of course, infrastructure auto-scaling based on actual container consumption, where we both help you place the given container on the instance, but we also help you monitor and right-size your existing containers. Just quickly to wrap it up before we jump into a demo. So this is a 3-layered approach to optimizing and automating your workload and your infrastructure. The first one is the pricing model. How we're going to pay for the instances, excess capacity, on demand, or reservations. Then we need to size them right. So the right size based on the pods that are required. We need to make sure that the pods are actually asking for what they need. With all three of those together, we can see clusters becoming significantly more effective. What we often see, just to share some of my experience, is that doing the instance sizing immediately means about 20 to 30% footprint reduction for any Kubernetes cluster we start touching. That alone, obviously, 20-30% less instances is 20 to 30% less cost. Out of the 70% or 80% that are left there, we're able to run most of it, if not all of it, on cloud providers' excess capacity, which will provide an additional 70 to 80% discount on what is left there. And then we can find some other defragmentation and optimization on the container utilization layer by helping the customer right-size their applications. A few of the other important things about Ocean. You can obviously run multiple workload types in the same cluster. It will do intelligent auto-scaling. It will have dynamic headroom, understanding the needs of your application and how much excess capacity it should maintain at any given time to maintain responsiveness at cost at the same time. It's aware of all your persistent volume claims and availability zones for specific applications, for your label stains and tolerations. These will always be taken into account when deciding how to defragment the cluster and making it as effective as it can be. We'll also provide you with the cost showback and cost breakdown to the inside of your Kubernetes cluster. How much are we paying per deployment? How much are we paying per namespace? And soon enough, you'll be able to filter your different tags and annotations in the cluster to understand how much they cost you on a per hour, weekly, or monthly basis. And this way you can easily charge back or understand which application teams are using more or less resources. And of course, as I mentioned, it supports every one of the Kubernetes engines. With that, I'm going to quickly jump into a live demo just to show you the console and what this looks like. So the first thing we see here is the general cluster information, the nodes running in it versus how many nodes are there total. The total instance hours it's been running over the last 30 days, what it would cost running as on demand, what it actually costs running a Spotinst in AWS in this case. So it's about $57,000 saved in a single month on that cluster, or about 63% of its cost. We get a detailed understanding of the pods running in it and the nodes registered in the cluster, the allocation of resources, as well as the productivity and change over time. The most important thing to see here is the instance distribution. This cluster mixes anything from a C5 4XL to an R3 large to a C5 18XL and M5 12. And anything in between, across a variety of families, instance types, and sizes. In this case, it's all running in a single availability zone. This specific cluster runs in 3 applications, one in each AZ. There are 3 different Kubernetes handling the same workload. We then get this cost showback, so we see our namespaces and the deployment in each one of them. And how much they are costing of the overall cluster on a day 7 or 30-day basis. We can export that data and obviously use it for whatever needs of the organization, as well as to run some additional filters if needed. And the right sizing, for pushing recommendations, we're seeing the deployments, the number of pods in the deployment. So I'll go back to the cost tab. I mentioned it in the cost. We get the cost showback broken down by deployments and namespaces, as well as some more detailed filtering coming up according to your labels and annotations to understanding how much each piece of the cluster is costing of the overall resources in it. And the right sizing, we help you right size the pods, as I mentioned. Sometimes there will be significant differences in the memory, in the CPU, but not in the memory. Sometimes it will be in both, and sometimes it will just be a minor change. But at scale, these things really add up to potentially thousands of dollars. Going forward, everything here is very much driven by how you look at a containerized cluster. So you start with your namespaces. You open every namespace. You can place the deployments in it. You can see what's happening in the deployment and modify it if needed. See all the labels and annotations it has, and all the pods running inside of it. From there, you can actually press one of these pods, get into the pods menus. You can see all the pod configuration, the host it's running in, the requests it has, again, the labels and annotations. If you look at the overall pods, you can also see your running, your pending, unscheduled, succeeded, and failed pods, as well as filter for all of them. And you can see the Spotinst cluster controller that helps do all this scaling and share that metadata with us so we can manage the, help manage the infrastructure of the cluster. Again, all your services and the namespaces, the nodes themselves, as we saw earlier. We get many different types of instances. M416 excels, 10 excels, our 524 excels, they're all very highly utilized and being packed efficiently to make sure the cluster resources are as utilized as possible. Cluster roles. Ocean also provides you with the ability to roll your cluster. You can mention why you did it. The batch size to have the cluster rolled in it. So once the cloud providers release an upgrade to Kubernetes, you have to upgrade all your workers. All you have to do is run an Ocean roll to make sure to drain, do it gracefully, and move from one node to another using the new config. Scaling, as I mentioned, completely automatic headroom, automatically enabled auto scaling based on pod requirements in real time. And launch specifications. So as I mentioned, a single Ocean cluster will allow you to run multiple launch specifications instead of having multiple scaling sets or auto scaling groups. You will have different node labels, stints, and tolerations, and you can change the launch specifications based on that need. And just to quickly look at some of the important things in the cluster. So the cluster really runs in a single region chosen by the customer. So choose the region and you tell us what is the existing cluster. We will pull in the VPC, the subnets. What you have to do is select which machine families are okay to run in your cluster in case there are some you're not interested in utilizing, just toggle them off. We choose the total number of resources just to make sure to give a long range here based on the different pods. And Spotinst will then build the matrix of options of what makes sense for that cluster. Obviously, pull the image, security groups, instance profiles, and key pairs. Then do the tags, the resource limits. Again, you want to think about resources like Kubernetes does. It does not care how many instances it has, but rather how many vCPUs and gigs of memory are available. Some additional configurations. And the important thing to see here, once we get to the summary page, that's all the configuration we needed. We press update or create. The Spotinst console will also build a Terraform for you with official cloud providers for Terraform with all the instance types this matrix has created. Or you can get it through JSON to run via the RESTful APIs. And that's it for the demo. And I think we'll open it now for Q&A.
Sure. So let's take a look at and see what questions have come in. We have a handful here. The first one here is, if the host OS is a Windows OS, the container build on top would be based off a Windows kernel. So why do we say we can plug this container anywhere? I mean, it won't work on a Linux distro. Is that correct?
Yeah, so that is correct. That's a great question. So that is kind of a edge case coming from the Windows world. Linux containers originated in the Linux space. Windows containers came a bit later. When we talk about the portability, we do tend in the industry to kind of default to the Linux side. It is interesting to know that with WSL and WSL2, that you can run Linux containers on both Linux and Windows. So a Linux container can actually run on both a host that is running Linux and or Windows. But you are correct that if it's based on a Windows OS specifically, that container is not going to be able to share a kernel space with a Linux host OS.
Okay. And then I have another question here that's directed at you directly, Kevin. Could you please explain how Spotinst is different from Rancher?
Absolutely. So we get this a lot, and we actually have really great integration with Rancher. So Spotinst is really focused on finding the best infrastructure to bring to the Kubernetes platform, and Rancher is really focused on how to run Kubernetes the best way possible for an enterprise organization. And the two fit well hand in hand. We actually have many customers today who use both our Rancher and Kubernetes integration, especially with Rancher 2, which is an awesome product out by Rancher. We integrate at the Kubernetes level to bring the infrastructure, and then we actually manipulate or call out to some of the Rancher APIs to make sure that the cordoning process and the node removals and the Rancher inventory is actually all kept up to date. So we look at as Rancher as a complement to what we do. And so for all the things that you can use Rancher for to get Kubernetes up and running, keep doing that today. And then if you want really efficient infrastructure to auto scale underneath it, Spotinst will plug right in and help you do that.
Okay. And then we have, looks like maybe one more question here. For AWS, do I need to configure my EKS first and then move it to Spotinst, or do I start by configuring it all on Spotinst?
So you could go about it both ways. There's actually a quick start on the AWS website to deploy EKS and Ocean together. It's basically a cloud formation that will deploy both of them with Ocean already wrapped around the worker nodes. Or you can have your existing EKS and we can wrap around it after you create it. Both ways, actually, I believe that deploying EKS directly through Spotinst and Work Console is probably one of the easiest way to do it today. It auto-fills a lot of the configurations for you, and it kind of walks you through what you need to do when. So it's a great thing to even start off with Kubernetes right on that. And we'll touch on it in a moment, but we do offer the first 20 nodes for free at no management cost at all. So very easy to kind of give this a free try.
Okay. All right, we're getting a little bit short on time here. So if you have any other questions, please get in touch by email, and you can see the emails there on your screen. If you have any questions, and we'll be certain to answer any other questions that come in as we wrap things up. Now, if you want to learn more about Kubernetes, what you can do is check out our Introduction to Kubernetes course on cloudacademy.com. By the end of that course, you'll be able to actually recognize and explain the Kubernetes service, be able to explain and implement a Kubernetes container, and then also know how to orchestrate and manage Kubernetes containers. For more information about optimizing cloud costs with Spot instances, be sure to check out the course that we've put together in collaboration with Spotinst. In this course, you'll learn how to leverage excess cloud capacity from providers like AWS, Microsoft Azure, and even Google Cloud Platform to optimize the costs of cloud computing using Spot instances. What this course does is teach you how to run and manage workloads on excess cloud capacity using Spot instances, how to explain the risks and benefits of the Spot market, and also how to recognize and implement Spot instances to reduce cloud compute costs. If you'd like to try Spotinst for free, visit the URL that you see on your screen. So that just about does it for today. I'd like to thank Kevin and Tomer once again for joining us, as well as all of you who've joined us today. Just a quick reminder that those who joined us today will receive the recorded webinar as soon as it's available. So thanks again, everyone, and have a good day.